Hello everybody, and welcome to section 5.1. We're talking about bisectors, medians, and altitudes of triangles. First one we're going to talk about is perpendicular bisector of a side of a triangle. And that is a line, segment, or ray that passes through the midpoint of the side and is perpendicular to that side. So here in this picture we see that. This blue line is perpendicular to one side of the triangle, and it is in fact a bisector as well. That means this side will be congruent to this side. Alright, and next up we're going to talk about Theorem 5.1. Any point on the perpendicular bisector of a segment is equidistant from the endpoints of the segment. Okay, so what this is saying is I have segment EF here, and all these points on the perpendicular bisector A, B, C, D, all these have the same distance from the endpoints. So EA congruent to FA, that distance is the same. EC is congruent to FC, and so forth. Alright, there's also sort of a converse to this theorem. Converse says any equidistant point from the endpoints of a segment lies on the perpendicular bisector of the segment. Okay, so it's the same picture, it's the same scenario. It's just we're going to start with the endpoints and say, okay, so EA, that distance, and that distance are the same, so therefore they must lie on this line, this perpendicular bisector that contains A, B, C, and D. Next up we have concurrent lines. Concurrent lines are when three or more lines intersect at a common point. We call these concurrent lines. A point of concurrency, it's the point of intersection of concurrent lines, or also known as the intersection point. So we got these three lines right here. Those are called concurrent lines. They're all meeting at the same point. This red point here is the point of concurrency. Alright, next let's talk about the circumcenter. Circumcenter is the point of concurrency of the perpendicular bisectors of a triangle. So here's a picture of all the perpendicular bisectors. Notice the notation for each of these. We know the 90-degree angle sign here. We also know that we are cutting each side in exactly 2 equal pieces, making the bisecting. And right in the middle here, where these 3 perpendicular bisectors intersect, that is known as the circumcenter. And we call that the circumcenter because a circle can be circumscribed around to touch the vertices of the triangle based on the circumcenter. Theorem goes with that, the circumcenter theorem. It says the circumcenter of a triangle is equidistant from the vertices of a triangle. So the distance from each vertex is the same. We'll show that here. Let's do that in a blue line. Let's say that here's the circumcenter, and we're going to go to the vertex right here. That vertex, and then that vertex, and that vertex. This theorem says all 3 of these blue lines here are the exact same. The distance is the same for all of them. Okay, moving on. Let's talk about angle bisectors. Okay, angle bisector of a triangle is an array that divides an angle into 2 congruent angles. So the green lines here, they are in fact bisecting each angle of the triangle. Okay, so we have right here, those 2 angles are congruent. Right here, these 2 angles are congruent. And here at angle A, those 2 angles are in fact congruent. Alright, another theorem. 2 theorems actually. We got theorem 5.4. It says any point on the angle bisector is equidistant from the sides of the triangle. So if I have a point on any of these angle bisectors, I know this is kind of small, but let's have a look here. Say I take this point right here. Then the distance from this point to each side of the angle that it's bisecting is exactly the same. Those 2 distances right there would be the same. And that is true for any point on any of the angle bisectors here. We can say it in the reverse order. We can say any point equidistant from the sides of an angle lies on the angle bisector. So it works kind of the same way. Alright, moving on. Let's talk about what's called the incenter. The incenter, the angle bisectors of a triangle are concurrent, and their point of concurrency is called the incenter of a triangle. Okay, so in this picture down here, we can see that we have angle bisectors coming off of each angle, and they're going all the way to a point on either side. They all intersect, and the point where they intersect here is called the incenter. Notice a circle can be inscribed within the triangle, and that kind of goes with the Incenter theorem here, 5-6. The incenter of a triangle is equidistant from each side of the triangle, and they are referring to points on the triangle in and around the incenter. So we're talking about this point right here, same distance from this point right here, which is the same distance from this point right here. Notice they're all touching the triangle there, and this incenter is the exact same distance for each of those. Basically, they form the radii of the inscribed triangle here. Alright, moving on. Next up, median of a triangle. This isn't too bad. The median of a triangle is a segment whose endpoints are a vertex of the triangle and the midpoint of the side opposite the vertex. So this is a median. We're not going to bisect the angle. We're just going to come from it, come down to the opposite side, and cut that opposite side in 2 equal parts. The median of a triangle. If we did that for all 3 angles and all 3 sides, if we took those 3 medians, the intersection of the medians would be what's called the centroid. Centroid is a point of concurrency for the medians of a triangle. I've been told that this is also the center of mass of a triangle. If we were to balance your triangle on the tip of a pen or pencil, it would be perfectly balanced at the centroid. Okay, moving on, we've got the Centroid Theorem. The Centroid Theorem says that the centroid of a triangle is located 2/3 of the distance from a vertex to the midpoint of the opposite side of the vertex on a median. So we'll illustrate that here. This is explaining this pretty well. We have AH, BJ, CG are medians of a triangle. They each join the vertex and the midpoint of the opposite side. The point of intersection of the medians is called the centroid. We know this, of triangle ABC. So here they're pointing out that AH, CG, and BJ are medians of the triangle. Then AN is 2/3 of AH. Okay, so here's AN. Let's point that out right here. And then AH, the entire side, entire length of that median goes all the way across. So what they're saying is the green distance here is exactly 2/3 of the red distance. AN is exactly 2/3 of AH. And the remaining side obviously is 1/3. So this, you can use this fact to help you solve some problems in determining what's the length of certain segments on medians of triangles. Okay, let's move on to our last slide here. Altitudes. Altitude of a triangle is a segment from a vertex to the line containing the opposite side and perpendicular to the line containing that side. So we got 3 scenarios here. Your altitudes, basically they start at a vertex and they drop straight down vertical or perpendicular, I should say, to the opposite side of the triangle. We're not bisecting it. On this picture here, BC is not cut in half evenly. But we do have an altitude coming down from A to its opposite side. Now say you have a right triangle, the altitude is the side of this triangle. It is actually the same as the side. We see the perpendicularity there. And on this obtuse triangle, we have an altitude that actually lies outside of the triangle. We start at this point here and we drop perpendicular straight down so it lines up with the opposite side. And lastly, if we take all the altitudes of all 3 sides of the triangle, let me show that these are altitudes, perpendicular, perpendicular, perpendicular. They would all intersect at what's called the orthocenter. The orthocenter is the intersection or point of concurrency of the altitudes of a triangle.